Turkcell Stratejik Pazarlama Müdürü Engin Çomakçı.
Efendim, öncelikle hepiniz hoş geldiniz tekrar. Bu salonda yaptığımız son seans. Ama teknoloji zirvesi 5'e kadar devam edecek. Hatta Maker Faire 6'ya kadar devam edecek. Bu seansta birazcık geleceği konuşacağız. Ama geleceği robotların ve sensörlerin dünyasından anlamaya, öngörmeye çalışacağız. Konuk konuşmacımız Qualcomm'dan Anthony Lewis. Birazdan ben sözü aslında ona vereceğim. O bize bu çip dünyasının robotları sensörlerle beraber nasıl değiştirdiğini ve robotların gelecekte hayatımızın nasıl içinde yer alacağını anlatmaya çalışacak. Onun sunumuna geçmeden önce ben çok kısa, konu gelecek olunca, Türkiye'de Turkcell olarak bizim başlattığımız bir gelecek programı var. Çok kısa onunla ilgili bilgi vererek başlamak istiyorum. Şimdi biliyorsunuz, geleceği öngörmek artık iş dünyası için bir zorunluluk. Çünkü önünüzü görmediğiniz bir yolda aslında hızlı da gidemezsiniz. Hangi yoldan gideceğinizi ancak geleceği gerçekten öngörürseniz, planlayabilirseniz gidebilirsiniz. İşte 2 gündür aslında gerçek zamanlı işletme döneminden bahsediyoruz. Gerçek zamanlı işletme olabilmek için de aslında geleceği öngörmek bu anlamda çok kritik. Peki geleceği öngörmek nasıl bir şey? Yani bununla ilgili ne yapmak gerekiyor? Evet, bu bir gerçek ama nasıl yapacağız bunu? En iyi yolu aslında geleceği öngörmenin, geleceği yaratmak, geleceği şekillendirmek. Çünkü geleceği içinde olursanız o çalışmanın, aslında gelecek geldiğinde zaten hazır olursunuz. Bunun için de geleceği yaratmak, geleceği şekillendirmek için de bugünden çalışmak gerekiyor. Ama bu tek başına olacak bir iş de değil. Yani siz bugün tek bir şirket, keza tek bir teknoloji şirketi olarak Turkcell bu işi tek başına yapamaz. Asıl kritik olan şey puzzle'ın parçalarını bir araya getirmek. Çünkü geleceği oluşturan birçok parametre var. Bunları masanın etrafında görüp hayata geçirebilmek. O yüzden Turkcell olarak başlattığımız ileri görüş programında sektör liderlerine, tüm iş ortaklarımıza, teknoloji şirketlerine ve bunların hepsini bir masada aslında toplayıp geleceği hayal etmeye çalışıyoruz. Hikayemiz geçen sene başladı demiştim. Geçen seneden beri 3 alana odaklandık. Eğer geleceği öngörecekseniz mutlaka odaklanmanız gerekiyor. Önce perakende ile başladık. Alışverişi değiştirecek trendlere baktık. Alışveriş dünyası nasıl değişecek önümüzdeki 5 yılda, hatta 10 yılda araştırmalar yaptık. Workshoplarla onlarca fikir ortaya çıkardık. Sonra pazarlamanın geleceğine baktık. Gerçek zamanlı pazarlamayı keşfettik. Nasıl şirketler gerçek pazarlama yapar? Buna öngörmeye, bunu göstermeye çalıştık. Ve son olarak da teknolojinin geleceği dedik. Çünkü teknoloji zirvesi bu son sayımızdı. Eylül ayında yayınladık bu raporumuzu. Madem ki teknoloji zirvesinde iş dünyasının teknolojiyle nasıl değişeceğini konuşacağız, teknolojinin nereye gittiğini de anlatalım diye aslında teknolojinin geleceği araştırmasını, çalışmasını yaptık. Bu çalışmayla beraber aslında onlarca fikir ortaya çıktı. Sabahleyin Michio Kaku ile başlamıştık. Hatırlarsanız Michio Kaku hep bize geleceği senaryolarla anlattı. Gelecekteki senaryoları bize hayal ettirmeye çalıştı. Aslında biz de ileri görüşte böyle yapıyoruz. Gelecekte teknolojinin nasıl geliştiğini, nasıl bizi değiştireceğini bu senaryolarla anlatmaya çalışıyoruz. Şimdi bu teknolojinin geleceğinde kritik konulardan birisi de robotlardı. Bugün zaten ana konumuz da o. Robotlarla ilgili kısa bir tespitimiz var aslında. Kısaca onu anlatmaya çalışacağım. Şimdi ilk önce robot dünyası aslında yeni bir kavram değil. Biz 1950'lerden sonra, yani bu endüstri devriminin ikinci evresinde robot işine girdik. Evet, robotlarla daha endüstriyel işleri yapmaya çalıştık. Ama bugünün dünyası aslında o dünyadan sonra daha robotları kişiselleştirdiğimiz ve daha sensörlerle algıları açık hale getirdiğimiz bir dönem. Bugün Qualcomm aslında çok önemli gelişmeler, çok önemli araştırmaları var. Onları anlatacak. Ama asıl hikaye next level bu robotların sosyal olmasıyla hayatımıza girecek. Yani bulut sayesinde ve network sayesinde biz aslında robotların daha akıllandığını, daha bizim içimizden biri haline geldiğini ve bizle beraber yaşama devam ettiğini göreceğiz. Ben lafı daha fazla uzatmadan Anthony'ye sözü vermek istiyorum. Teşekkür ediyorum. Umarım çok ilham verici bir seans dinlemiş olursunuz. Anthony, the stage is yours.
Thank you very much and welcome. And thank you very much for staying to the last session of the conference. I know a lot of people don't know a lot about Qualcomm, so I'd like to begin this presentation with a video showing an overview of what we do. So if we could roll the video right now, I'd appreciate it. Video?
Kids can use the tablet to bring Legos to life.
Did you see that?
See the bit distribution? Yeah, we can bring that down.
All right, thank you. So I love robots. And what I think is that mobile computing technology can have a huge impact on the next generation of robots. These are robots that are not going to be used necessarily in factories, but are going to be taken out of the factories and put into homes, put into places where they can help people with everyday living. And if you take a look at this picture, you see two technologies which seem to be very different. You have the mobile phone, and you have a robot. This happens to be our robot we call our Snapdragon Rover. And they seem to be very different, but under the hood, they have a lot of the same processing requirements. Heterogeneous computing is one. So what does heterogeneous computing give you? What does it mean? People are familiar with the term CPU, which is used inside, say, your desktop computer. That particular type of computing is rather general purpose and can be used to compute anything you want. But when you try to put things into a mobile computing environment, you have to optimize for speed, for processing power, for energy, etc. And this naturally leads to the use of multiple types of computing cores. You might use a graphics computing core for doing graphics rendering. You might use a digital signal processor for audio processing. You might use your CPU for running your applications for browsing the web. So you're going to need heterogeneous computing. The same thing with the robot. The robot's going to need to be able to run regular applications, to be able to make decisions, to do things. It's going to have to do intense processing of perceptual information, and this can leverage GPUs. It's going to have to process auditory information as well, DSPs. So a heterogeneous computing environment is ideal for robotics as well as for mobile. You need to be able to process vision and audio. Now for vision, most people think of vision, they think of a camera, The camera is used to take pictures, but it can also be used as a sensor. It can also be used to understand the world around you. And so we'll show you some examples of how you can use a camera to understand who you're taking a picture of, and perhaps automatically send a photograph of whoever appears in your picture to their email addresses. You also want to process audio, etc. For a robot, it's similar. You want to be able to understand the world around you, and you want to do this with high performance, high speed. Navigation. You need one of the biggest uses of mobile devices right now is determining where you are. Now, this works fantastically well, especially in GPS-enabled environments. Sometimes when you're in very crowded cities, you're indoors, etc., you're in GPS-denied environments where you can't rely on GPS. Other solutions have to be taken into account. So just like in mobile, robots as well are going to need to know where they are, particularly inside buildings. And so the technology that we have developed for mobile platforms can be directly translated to robotic applications. Machine learning is really at the cutting edge of new technology for mobile devices. Machine learning can be used for detecting various threats, viruses, etc. But machine learning can also be used to enhance the perceptual capabilities of your phone. So when you want to recognize that face, when you want to determine what I'm taking a picture of, say I'm taking a picture of food, you want to be able to adjust the camera settings automatically, you're going to need to use very sophisticated computer vision processing in order to enable that capability. And that capability is going to rely on machine learning. And I'll show you some examples of how we can do that. Of course, wireless. A mobile device wouldn't be very good if it was tethered, would it? And neither would a mobile robot. So as robots move out of the factory into the homes, they're going to need to be untethered. And finally, power management is essential for mobile phones. So a mobile phone contains an amazing amount of energy, enough energy to lift average-sized person about 7 floors straight up. That's how much energy it has. But still, even with that amount of energy in the battery pack, you still have to use that energy very wisely so that your mobile device will last for a long time. Same thing with a robot. Now, it may seem counterintuitive. A robot is mechanical. It uses lots of power. That's true. But if you look at the power requirements and look at the division of power between computing and the actual movement of the robot, some vendors are reporting that it takes about 60% of the power budget goes to just the computation alone. So 60%, 40% to moving the robot, 60% to actually thinking about moving. And so there's a great need for very efficient, high-performance processing, especially in robotics. Okay, so what I'm going to try to do is to tell you a little bit of a story about heterogeneous computing, why it arose, how sensors are driving the evolution of computing and making devices much more high performance, and some advanced sensors, and thinking of sensors in ways you might not think of sensors. So thinking of a camera as a sensor, a visual sensor, thinking of audio as a type of sensor so that your device can wake up and understand your commands when you're talking. So I'll talk a little bit about that. Then I'll talk about our Zeroth perceptual processing research. So what the Zeroth perceptual processor does is it leverages machine learning, cutting edge, called deep machine learning. I'll describe that in a little bit. And it's going to be able to put that onto your mobile device. So currently, you may not know it, but you're probably using deep learning when you interact with your mobile device. When you go to Google now, and you ask Google to do something, the voice recognition is remarkably good based on deep learning. If you look at the way figures, objects, things are tagged in images, that often is based upon deep learning, and that usually is put into the cloud. But by building a specialized processor engine, we hope to be able to put that into your mobile device as well. And then I'll show you how we can wrap all this together into a robotic application. Okay, so where is this coming from? So the driving force is really consumers. Consumers want their mobile device to do not just make phone calls, but to do everything else. So it becomes a way of getting your morning paper from various cloud services. You can text people, you can obviously use voice. You can also take videos. You can watch videos. You're on the airplane. You want to watch the latest Hollywood blockbuster. You can do that on your application. You can play very high-end video games, which are almost as good as console games were a few years ago. Now, that requires a tremendous amount of processing power, and it has to run unplugged in a mobile device with a limited amount of computing power. You also look at the adaptation of sensors. So over the last few years, this is you're using Samsung as an example. There's been a rapid adaptation of more and more sensors, about 2 per year roughly, over the last several years. And so if you think about it, why is there such a rapid adaptation of sensors? And why do people care? Well, you can only do so much in terms of processing power, and you can only create a distinction in your product so much by increasing, say, the processing power of your device. If you add a sensor onto your mobile device, you're now able to not just do, you're able to do something fundamentally different than you could do before. So if you have a heart rate sensor, you can now measure your heart rate, where before, no matter how much computational power you had, you're unable to do that. So adding sensors adds new capability and allows vendors to distinguish themselves from previous devices. So there's been a big push towards more and more sensors. Now, as those sensors have become available, as we've also increased the processing power, we've enabled new ways of using traditional sensors. So you want to know the user's location. You can do that with GPS, but you can also do that with Wi-Fi, using Wi-Fi in a different way than you might be used to, using Wi-Fi in combination with accelerometer and gyroscopes, which were perhaps originally used for gaming. You can sense the user's motion, again, using accelerometers and gyroscopes that might have been used for gaming before, or just to orient the display on a tablet. You can now use that to sense what a person is doing and when they're doing it. You can see the user's environment. So using a camera, which was probably originally used to take pictures, you can now use it to see and understand the environment in a very smart way, and to overlay an augmented reality onto that environment to create marvelous new ways of representing data that were not available before. And you can also hear the surroundings. So you want to be able to use your microphone not only to transmit voice messages to your friends, but also to allow the phone to wake up on your command and execute actions when you're at almost any time. As a result of this, there's been a lot more sensors have been adopted, more algorithms have been put into place with more and more demanding applications. So before, several years ago, maybe an algorithm would run with a single sensor. Now, the norm is for an algorithm to process data from several sensors at once. This requires more and more computational power in order to support these new and improved algorithms. Now, when you look at the algorithms which can be run, you can there are probably 4 attributes that you want to look at. You want to look at the performance, high-performance algorithms. This would, by having high-performance power in your processor, you're obviously able to process many sensors simultaneously, but also sensors like non-traditional sensors like cameras, etc. You want everything to work at low power. Again, the theme of low power comes back again and again. But this all becomes very, very important when you're trying to achieve always-on sensing. So what does always-on sensing do? So this means that when the phone is in standby, it's idling, it's able to still sense what the user is doing. So it's able to sense whether the user is walking, whether the user is sitting in a car, etc. And it's able to use that information intelligently. And it needs to do that without impacting the standby time of the mobile device. And so that requires very clever algorithms plus computation, hardware computation in order to get that done. And it has to be responsive. And so this is called real-time processing. Real-time can occur at several different levels. One is in the sampling of sensor channels, and the second one is when you're interacting with the user. You don't want things to lag behind. When you're painting an image over your camera input, you don't want there to be a noticeable lag between the drawing and the acquisition of the image. So this has led to the development of several different types of computational engines. So you have CPUs, and those are best for things like browsing, for things that require a lot of decision making. You have digital signal processors. Those are remarkable because they use very little chip space. They're able to run at very low power, and they're really ideal for processing scalar signals like microphones, etc., gyros, accelerometers. You also have other types of data. You have, if you want to paint a display, then you have a lot of data which is coming in, and all the data has to be treated in a very similar way. This allows you to use highly parallel processing architectures as embodied by GPUs or graphical processing units. And those GPUs can be repurposed for doing things like visual processing as well. Okay, now we can put everything together into one little package. This is very nice when you're trying to build a device which is low cost, which is compact. So inside our typical Snapdragon processor, you might find a CPU, a GPU, DSPs, wireless communication ability, multimedia, a display, LCD, all packaged in one unit, plus a unit which will process your sensory data. As opposed to having maybe a separate chip, you can repurpose existing hardware to process sensory data all in one integrated environment, reducing your part count. Navigation, and in the future, we hope to put a thing which we call an NPU. So in addition to a CPU, GPU, DSP, an NPU, which would be our neural processing unit. Okay, so let's give an example of how we might use this, like the processing stream that might be necessary to do some sort of real-time computation of a sensory stream. You want to be able to, one, receive your sensory data. You have to do that with a very regular sampling rate. A DSP might be ideal for that. You want to run your algorithm, which is going to convert the raw data into useful information. Again, a DSP might be excellent in doing this. You want to make decisions. You might enroll the capabilities of another processor. And then you want to provide instant feedback at a very rapid rate. Now, the same technology can also be used to enable the Internet of Things, which is basically the idea of taking the entire world and embedding processors into the world and wireless capability to allow the world to become active and be able to control and sense. And the market for this Internet of Everything, Internet of Things, is expected to be vast. So it represents an enormous capability, enormous promise. Let's go to that. Okay. I'll talk to you a little bit about the future of sensors. Okay, so we're familiar with GPS. One interesting trend in sensors is to take an existing capability and then repurpose it as a sensor. So in this case, we're taking Wi-Fi and using it as a way of locating ourselves within a building. And so this might be very important if you're going into, say, a hospital with lots of doctor's offices and lots of suites that you've never been there before. You want to be able to navigate from the entryway to the proper office. So you might be able to, you'd want to be able to do that with your phone. But using a phone that's based on just GPS, you're probably in a GPS environment which is not so good. You wouldn't be able to do that. So there's ways of using the Wi-Fi information itself to navigate. And so this is an example of a technology that Qualcomm has developed. We're using a combination of Wi-Fi information, accelerometers, gyroscopes, as well as a map of the building. The little dot represents where the phone is thought to be. The circle represents the air. And so you can imagine that this could be used to guide someone through a very complex building. It might also be used to serve up ads as you're walking through a mall. It's up to you what it's used for. But this is an example of technology which allows you to know where you are even when GPS is not available. Okay, this technology is based upon using a camera as a sensor. So here we're using a camera to track feature points in the image, and the user is walking through a corridor about 300 meters or so, and using vision alone. Now across the screen is a trail of breadcrumbs, and that indicates where the device thinks it is. And as it's moving through the environment, it's going around a closed circuit course and then coming back to where it began. And it can come back, and the error, when it finally reaches home, is within a meter or so. So this is using vision alone, vision which is used to take pictures, etc., being repurposed as a device to localize you indoors. Okay. I'll talk a little bit about Zeroth. So Zeroth is really a new project based on brain-inspired computing. And the idea is to try to achieve some of the power efficiency of a human brain. So a human brain uses about 20 watts of power. If you try to simulate a human brain, it's estimated that it would take about 200 megawatts of power to simulate a human brain using existing processors. So clearly, if you're trying to get the sort of processing power you might see in humans, the sort of perceptual processing power, it's going to take a new architecture in order to achieve that. Otherwise, it's just going to be too big, too costly. It's going to be impossible to achieve using conventional processors. The Zeroth program is a combination of three related scientific regions. We have computational neuroscience, where we study the brain. So we have a team of neuroscientists who look at cutting-edge findings in the brain and try to figure out how we can translate how people understand how the brain works, how the brain thinks, into practical technical devices. There's neuromorphic engineering. This is the science of building new architectures, new ways of creating computation that are very different than the CPU architecture, which I mentioned before. Very different than what's called a Turing architecture. We also have deep machine learning. This is a very new technology, becoming very popular since about 2008 onwards, where we've had breakthrough after breakthrough showing how we can beat state-of-the-art in conventional computer vision and related sciences. And by combining these together, we hope to be able to create a very low-power, high-performance perceptual processor. Okay, so we're going to use a different approach to the way we do hardware. And so if you look at a conventional CPU, it excels at high-speed data movement. It's always going to be high precision. It's going to have a low degree of parallelism, no matter how many cores you put on board. It's optimized for arithmetic computation, for addition, subtraction, multiplication, and division. In fact, if you go back about 60 years and you use the term computer, what people would think is that you're talking about a group of individuals in a room operating an adding machine, doing some sort of scientific calculations. So those were human computers, which have been replaced by our silicon versions. But basically, these silicon versions are mimicking what people used to do with adding machines. As I've said before, this sort of technique is very inefficient for brain-inspired computing. So we're looking at different brain-inspired technology, which will minimize data movement, won't need the same precision that you have in conventional processors, and it should lead us to very efficient brain-inspired computing. We're going to combine this with what's called deep learning. This is relatively a new breakthrough approach in the way that we can do perceptual processing. Up until this point, if you wanted to do perceptual processing, if you wanted to understand language, you wanted to understand what's in an image, you'd have, you'd have data coming in, you'd handcraft features. So individuals would spend decades coming up with ways of analyzing an image, analyzing an audio channel. Then this would be put into what's called a classifier, a way of taking this symbol of features that you've extracted from your data, and then coming up with a conclusion about what you're seeing, what you're listening to. With deep learning, instead of handcrafting features over decades, you can actually learn those features, and this can be done very quickly. in the matter, relatively speaking, in the matter of days or weeks. And we can then achieve better than state-of-the-art performance or state-of-the-art performance on many tasks. So this is an example of the use of deep learning as an engine. So when I say deep learning as an engine, what I mean is that you're going to be able to apply deep learning to many different tasks. So not just one task. So this particular task is a task in face recognition. So being able to recognize a person's face. What's different here is that it's relatively robust to the orientation of the individual versus algorithms that you see now. What's remarkable is that the same algorithm, the same processing, can be used to do things like recognize objects. It can be used to recognize scenes. It can be used to listen and understand voices. So the same computational structure can be used for all those things. And this is what makes deep learning so promising and so powerful. So this is an example of a application on a phone. So what's going on is the phone has identified each person in the photograph. And this is without going to the cloud, without taking the person's image and sending it to the cloud. This processing is all done locally and in real time, as you're seeing here. Using the same technology, as our speaker mentioned, or as one of our speakers mentioned earlier this morning, you could then pull up all the information that you want about this individual. You can pull up their LinkedIn profile, their Facebook profile, et cetera, all in real time. So this is a very powerful technology. And the same technology, we've demonstrated it being used to do scene recognition, object detection, object recognition as well. And the hope is that we take one of these NPUs and it'll find a home amongst all our other processing. So in addition to CPUs, GPUs, DSPs, NPU might sit in your processor as well. Now, let's see if we can put all this stuff together. So the topic of the talk was robotics and mobile. So this is an example of putting everything together. So we have our Snapdragon robot. Inside the Snapdragon robot, we're running a Snapdragon 600 processor. We're using the DSP on board the processor for motor control. We have accelerometers, gyroscopes, all the same quality that you might see inside a mobile device. We have Wi-Fi and Bluetooth. This is all computing, all controlling actuators. So there's 22 force-controlled actuators. There's an RGB camera, and there's also a depth camera. So one of the things that's coming out now, one of the things that people are really becoming interested in is 3D perceptual awareness on mobile devices. And so we're using one of those sensors on board this Snapdragon rover to understand the three-dimensional structure of the environment. Okay. Now, suppose you want to clean up your kid's room. Now, if your kid is like my kid, he isn't the cleanest person in the world. The room is going to be a little bit messy. You would like to be able to take your Rumba robot, drop it into the room, press the button, and have it clean the carpet. But the reality is you have to pick up everything first. What you really want is a robot that'll do that decluttering for you. And so this is an example of a robot that might be able to do that. This robot uses deep learning and neuromorphic techniques to be able to recognize objects in real time. It's then able to take instructions from the parent as to where that object should go. The one interesting feature of this deep learning is that it can generalize. So when you show it a picture of one action figure, it can generalize to many action figures. And so you don't have to train on every object that you want. You just have to train it on the class of object that you want to recognize. And so again, this is using the mobile processing power that you'd find on a typical smartphone, along with advanced sensors. So it's remarkable that we've come this far with our processors. If you go back in time about a decade, 2003, there was a thing called the DARPA Grand Challenge. This was sponsored by a research organization in the United States. And the idea there was to create a car that could navigate across the desert autonomously without any human intervention. What's remarkable is a processor that any of you probably have on your person right now is more powerful than the processor that was used to drive the winning entry. And so in the course of just 10 years, we've gone from something that was really magical and science fiction that was that could only be enabled by the highest degree of processing power, and that can now be dropped into your pocket. And so we're truly living in this magical age. People haven't really figured out how to incorporate this new processing power, these new sensors, et cetera, into robotics. But I think when they do, we're going to enable a whole new world of mobile robotics. Thank you.
Okay. Bu son seansımızdı bu salondaki ama 6'da hepinizi Sezen Aksu'ya tekrar bekliyoruz. Görüşmek üzere. İyi akşamlar.